All right, class. With this worksheet here, we're given this example problem, and notice once again I go through and I underline the key terms that are in this. And as I see, I have this rubber stopper with a mass that's attached to this 0.93 meter string and making one revolution 1.18 seconds. So what we're dealing with is we're having something that is rotating around with this radial distance r, and it's this mass that's out at this distance, and it's moving with this velocity v, and it's being held onto the string, causing it to go in a circle. And what we're trying to find is that tension force from this string acting on this mass. This is very similar to what the students were doing in a laboratory experiment. So we know the centripetal force is this mv squared on r. We know the mass. We know this radial distance r. We know the time t is this 1.18 seconds. We know the velocity is the distance over the time. The distance it takes is the circumference, 2 pi r. And divided by that time, we get this velocity to be this 3.2 meters per second. That's the speed it goes as it goes in orbit. We know the centripetal force is the force making it go in a circle. The force is actually this tension that's making it go in the circle. Doing mv squared on r, we get this 0.22 newtons. As I look to this number 1, similar here to where we have this runner moving at this speed of 8.8 meters per second and this radius 25 meters. And so once again, we have this person running. We have the center of this circle here. The force is centripetal going towards the center. This acceleration goes in the same direction, and the velocity is perpendicular. We know the centripetal acceleration is v squared on r. We know the v, we know the r, so we can get this as a 3.1 meters per second squared. And it's coming from the friction. So this centripetal force is due to friction. So this friction causes this runner to accelerate towards the center of this circle at 3.1 meters per second squared. Same thing with a race car. We know a car racing on a flat track with this speed on this radius is going to operate in this same thing, where its centripetal force is really that force of friction pointed towards the center. And we're asked to find its centripetal acceleration, v squared on r. V squared on r, we get this 8.6 meters per second squared. What we're asked to find is this minimum coefficient of friction. I know the centripetal force is acting towards the center of the circle. So if I then look at the free body diagram for the car, I have this mg down, the gravity, the force due to gravity acting on the car down, and the normal force up. So the car is on the road with this friction causing it to turn. I know the force of friction is mu times the normal force, and what we're trying to find is this coefficient mu. So if I look at my free body diagram, the force due to friction is the only thing here making it go in a circle. So this force due to friction is making this mass go into a circle. The force due to friction is the net force. Force due to friction is mass times acceleration then. And the way it reads is force of friction makes the mass go in a circle. That's the way I read this. I know the force due to friction is mu times the normal force, still equals to m times the centripetal acceleration. So mu times the normal force, which is mg, if I know the normal force up and the mg down, they are equal to one another because the net force in the y direction is 0. So normal minus mg equals 0. Therefore, normal equals mg. So mu mg equals mac. So I divide by mg on both sides. The mass cancels out, so the mass doesn't have anything to do with this, how rough the road is. That's what this coefficient is, giving us this centripetal acceleration divided by g. The centripetal acceleration we had from before is that 8.6. The g, I'm going to use the accepted value of 9.81. We could also use 10 if we were asked this on a test. So it would be 8.6 divided by 10. You can get 0.86 or 0.88 if you use 9.81. So I look to the backside. What we're asking here is with this airplane traveling at 200 meters per second, we want to know this radius to keep the centripetal acceleration under this 5.0 meters per second squared. I know v squared, I know r. Actually, rather, I'm trying to get r. So r is v squared on the centripetal acceleration. I have v, I have the centripetal acceleration. And when I get this 8,080 meters, but I only have 2 digits given here, so I round up to 2 digits here, so it's 8,100 meters for this radius r. Lastly, I have a merry-go-round, so a 45 kilogram mass on a 6.3 meter radius. If we have a speed of 4.1 meters per second, we're asking about this force of friction. The force of friction is the object's force causing it to go in a circle, so that's what we're trying to find. So this force of friction is this centripetal force, which is mass times v squared on r. We know the mass, we know v, square it, divided by r. And reporting in the 2 digits, we get 120 newtons.